Hello there, I am Pramod Buchunde and I am recording this video for the assignment number 1 of course EE769. We have given 5 tasks and these are the tasks. First task is on likelihood and loss, second building nuts and bolts, and then optimization and estimations, the bias variance experiment, and then regularization behavior, and then the bonus model. So I have covered all these tasks. Okay, so we will see one by one. Okay, I will start with the likelihood and loss. So I have make a PDF for this particular task. So this is my uh, the task number 1. So this is the question: show using derivation that maximizing likelihood under Laplacian error leads to minimizing mean absolute error. Okay, so maximizing likelihood under Laplacian that leading to the minimizing mean absolute error. Okay, this is the actual value, this is the predicted value, and this is the error. Okay, so we have to reach to the predicted value should be reached to the actual value. Okay, so for that we are using the Laplace error. So it is a Laplace distribution center at 0, and this is the parameters, right? Yes. And this is the probability of the error. Okay, so probability of occurrence of this error is given by this expressions. So this is nothing but the probability density function. Now when we are applying the conditional probability of that output, then the conditional probability of single sample would be given by this expression, and then we are summing up, we are multiplying this the probability distributions for an independent observation. That is nothing but our, we will get the likelihood functions, and that functions we have to maximize, right? So this is the likelihood function. And if we are using the log on both sides, so if we are using the log, it is easy to optimize. So we have used the log over here. So the expressions would be, these expressions would be coming down to these one. Okay, so this is nothing but the constant part with respect to weight, and we have to maximize these weight functions. Okay, likelihood, we can say that the likelihood functions. Okay, so that the maximization of that likelihood function is depend on this expression, and this expression is negative, and we have to maximize this likelihood function. Okay, when we are maximizing the some negative terms expressions. Okay, so basically what we are doing, we are maximizing the likelihood function. It means that we are minimizing these expressions, right? So maximizing negative expressions equals to minimizing positive ones. So here maximizing a log, there should be the log. Okay, so minimizing this one is nothing but the mean absolute error. So okay, so that satisfied our question. Next question is identify the step in the derivations where the modeling assumption directly determine the objective. What would change if the assumption change, right? Okay, so assumptions comes into the pictures at the step where the probability distribution of the error term is specified, right? So for the Laplacian error, the expressions would be different. This is the expression for the Laplacian error, and this is the expression for the Gaussian error. Okay, so derivation is basically the same derivation is there. Okay, but the output will be different. Okay, if there is the Gaussian error, then the output would be the MSE, and there is the Laplacian error, then the output would be the MAE. Okay, so what will happen if the say this is the mean square error and this is the mean absolute error? What will happen? So okay, the penalization of the weights is different in the MSE and MAE, and MSE is more sensitive to the outliers, and MAE is robust to the outliers. So basically when we are choosing the Gaussian error or Laplacian error, we should be cautious. Right. Next question is, if the error distributions become heavier tail than Laplacian, what quality change do you expect in the loss functions? Okay, basically the loss functions, our loss functions, likelihood functions is equal to the negative log of the probability density functions of the error, right? So as it is the heavier tail than the Laplacian is actually the leptokurtic, it has the long tail. Okay, and if we are, and Gaussian is have a light tail. Okay, so Laplacian have the kurtosis greater than 3, okay, much greater than the 3, and then we are using the heavier tail. It means that the probability of the error decaying is slower, as that residuals is tending to the infinity, then it will gives the very slow response to that. Okay, so grows the error, if the error is more, then it will grows very slowly, right? So the loss becomes sublinear in the tails, very sublinear in the tails, okay, very in robust to the tails, right? Outliers, right? The influence of large residual is bounded or diminishing. Now, that will be the diminishing or very bounded. Okay, from the mathematical expression you can see that, okay, as the residuals is tending to infinity, then the gradient is tending to the 0, right? So it is the sublinear growth actually, right? So in the heavy tail it is very sublinear growth, very slow growth, okay. Decaying rate is very slow, right? In case of Gaussians it is different, and it is the square of the error, and it is the is equal to the absolute of the error, right? Next question is, given only training data, describe a procedure to devise whether MAC or MAE should be minimized. Justify each step. Okay. So as we are using the MAC MAE, right? So when we are differentiating MAC and MAE, so we have to, by looking at the training data, it is not possible. Okay. So what we have to do, we have to find out the residuals. First we have to compute the residuals. After computation of the residuals, we have to draw the histograms and QQ plot or kurtosis, value of the kurtosis, and from that we can decide whether we have to use the MSc or ME. Okay, right? If there is the leptokurtic, right? Approximately Gaussians, then the tail is light, error or light tail, right? So here you will see that the kurtosis is equal to 3, right? Okay, so these two things, and histogram you will see that the normal distributions, light tail histograms you will see. Okay, QQ plot, in that QQ plot most of the residuals are closer to the prediction line, but in case of the heavier tail leptokurtic, so you will find that the when you draw the QQ plot, then so you will find that the lines, okay, predicted lines, the outlier are some outliers are very far from that predicted line. So okay, and histogram would be heavier tail, right? Long tail histograms you will say leptokurtic. Okay, it means that the kurtosis is greater than 3. Okay, right? So first, given training data, what we have to do, compute the residuals and then draw the histogram or QQ plot and empirical kurtosis. So from that things, outlier proportions, see the outliers, how many outliers are uh, there, and based on that we can take a decision that we have to use the Gaussian error, or we have to use the Laplacian error. Okay, what kind of noise are there, right? So from there that will be clear. Okay, so this is nothing but this is all about the first step. I have covered all the points, and then we will move to the next part, right? See, building nuts and bolts. Okay, so first we have to see the covariance matrix, and then we will move ahead, right? So here for the first part, okay, yeah, this is the first part, right? Okay, so right. Okay, this is nothing but just the building nuts and bolts in Pythons, right? You will see that implement n data generator. We are generating the n samples. So inputs are n sample, covariance matrix, weight vector, error distribution, and error distribution parameter, right? So here you will find that the each features marginally standard normal. I have used only the two features, right? And then I have found out the covariance matrix. I have validated that covariance matrix. Here you will see the validation of the covariance matrix, and then I have added the one extra weight column for the bias, and I have plotted the ideal versus noisy output, right? So when noisy output with respect to Gaussian, with respect to Laplacian, with respect to the uniform noise, okay, right, right. Now when I have run this code, this is the first they validate covariance matrix. So covariance matrix must be square, it will satisfy that. Covariance matrix must be symmetric, it will satisfy that. Covariance matrix must be positive semi-infinite, it will satisfy that. Diagonal element must be 1, right? So it is validating, this function is validating basically to the covariance matrix, right? And then I have generated the data, number of samples randomly I have generated, and then I have finding out that what will be its uh, ideal output with the noisy output, right? When we are using the Gaussian, when we are using the Laplacian, when we are using the uniform, what will be its QQ plot, what will be its noisy actually ideal versus noisy output, that is we are going to see, right? So run this code. After running this code we will get the uh, right, okay, see, this is nothing but by looking only these things, okay, most of the residuals are very sticks to the that predicted line. So it is more or less nothing but the plot of, this is the ideal output and noisy output, but this is the plot of the uniform. Okay, let's check, it is the plot of the uniform error type, right? It is the uniform error type plot. Okay, if we are changing these things to the Gaussian or Laplacian, okay, let's change it to the Gaussian. Okay, so at Gaussian, okay, this is the uniform thing, so let's see, it is sticking, right? So in the Gaussian you will find that some kind of the residuals are far from, are away from that predicted line, okay, than this one. Okay, so if we are running these things, then let's see the plot, what will be the plot of it. Okay, so this is the plot where you will see, okay, it is converges, okay, it is converges about this predicted line, but as compared to the uniform, it is that residuals are quite away, okay, as compared to the uniform. Now when we are comparing with the Laplacian, then you will find clearly, you will see the outlier. Okay, there are some outliers, you will clearly see the outlier. Okay, so when we are running it, right here you will see the clearly outlier. Okay, so uniform, Gaussians and Laplacians, we have seen the ideal output to the noisy output when we are changing the errors, right? Now we will move to the next part, and that next part is what is the two negatively correlated features, right? Okay, so we will see that show at least one visualization of two negatively correlated features. What is mean by two negatively correlated features? Okay, so firstly, negative correlated features, if we are giving the example that the speed is increasing and the time is decreasing, if you want to give another example, then the demand is increases, then the supply will be reduces, supply will be increases, then the demand will be reduces, then there is the vice versa. Okay, inversely proportional in between the features, right? So how can we understand this relationship? Okay, that relationship can be understood by finding the covariance matrix. Okay, if you see that the diagonal elements, right, and in the other than the diagonal elements, okay, if it is the I am using only the two features, so these would be the P would be the negative is less than the 0. If we are using the more than two features, then some of the 1 PQ, like, okay, if you are using more than the two features, then the some of the features are negative and some of the features are the positives, right? From that we can derive the inference that the some are the negatively correlated, right? So that condition has to be satisfied, this condition, okay, this condition has to be satisfied for the negatively correlated. Okay, and the graph, if we plot the graph, then the graph will be show as the downward linear pattern. Okay, if we run this code, then that code, okay, will clear everything, right? So here you will find that it is the, okay, it is going downward, right? So this is the feature x1 and this is the feature x2, there is the downward relations. Okay, if it is the feature x2 is increasing, then the feature x1 is decreasing, right? If the feature x1 is decreasing, then you will see that the feature x1 is increasing, then you will see that the feature x is decreasing, right? This is the value, right? So this is the case for the negatively correlated features. Then we will move to the next problem, right? Next questions, right? So this is nothing but the 2.3 gradient descent it is covering, right? It is covering both the things, right? It is here, okay. Implement gradient descent with L1 L2 regularization, also implement gradient descent with L1 and L2 regularization, okay. So this will be covering both the things, right? L1 and L2 regularization. When we are using L1 regularization and when we are using L2 regularization, so if L2 regularizations L1 L2 regularizations, okay, for the penalty purpose of the, for the penalty of the weights, we for the penalty of the weights, okay, for the we use the L1 and L2 regularization, okay. That L2 regularization penalizes large weight, and it penalizes mildly to the small weights, okay. But what happened with the L1 regularization, in the with the L1 regularization, that L1 regularization eliminate the features, right? So it is works on the sparsity. Sparsity means that the some weights are exactly equal to zero, right? Nearly equal to zero, okay. If the weights is equal to zero, then the features is automatically eliminated, right? So there is the feature selections, okay. L1 only select those features which has the large correlations, right? So this is nothing but this is the loss functions, and if we are, this is the loss function of the L2 regularizations, okay. So when we are taking the gradient, so gradient of that bias and the gradient weight of the weights, you will get these things, right? And when we are using the L1 regularization, that is also called the lasso, and this also called the ridge model, right? Then this is the for bias, and this is the weights, right? So when you are using gradient descent with L2 regularizations, update weights using the square weight penalty to shrink coefficients smoothly, okay. While gradient descent with L1 regularizations were the absolute weight penalty, and this and weight exactly to zero. Some weights are exactly to the zero. That is nothing but the sparse, okay. With the in both the case, bias terms are excluded, okay. So L2 penalizes large weight, right? Strongly penalizes to the large weight, but mildly penalizes the small weight, okay. L2 doesn't create the sharp corners, but in case of the L1, it creates the sharp corners, okay. So features get completely eliminated in L1 cases, and model automatically performs feature selections. How that will be eliminated, see, okay. Right here you will find that the L1 is the diamond shape, okay, constraint. L1 constraint forms a diamond shape regions, okay. So square error contours are ellipses. When the ellipses touch the diamonds at the axis, that makes the weights zero, and that weight is assigned to some features. That features is automatically eliminated, okay. So when we are using the ordinary least square, feed data exactly even if unstable, right? So ordinary least squares, the data fit, okay, exactly data fit, but what happens, the every time when you are going to run, it assigns the different rate, because that gives the number of solutions, right? Sometimes it gives the number of, that is the possibility that it gives the number of solutions, okay. So it is unstable model, right? Or ordinary least square, okay. This is the stable model, both the things are the stable, but here use all features but gently, okay. L2 regularization uses all features but gently, but L1 regularization eliminates some features, so only most important features it is select, okay. Right, when you are running this code, right, so we will get the L2 regularization. So this is the number of iterations, so and the loss is coming down as the iterations increases. L1 regulations are the loss is coming down when the iterations changes. Here you will see some weights in the L1 regularization is nearly equal to zero, right? Here you will see that this is nearly equal to zero. Here you will see that this is nearly equal to zero, and here, and this is the bias, okay. Bias is more or less is same, right, in both the case, because bias is excluded, right? So in this case you will see that, okay, it is penalizes okay, for the less it is penalizes mildly, right? Here you will see that this is the true weights. At the start we have assigned the weights, and that assigned weights is coming down, right? For the L2 and L1, right? It is coming down to this, it is coming down to this, it doesn't it has excluded, basically we can say that it is excluded, but some weights is assigned here, okay, in L2 regularization. some weights is it is penalizes mildly. Okay, so here it is also added the weight, right? But in case L1 model, it is nearly equal to 0, it is nearly equal to 0. Okay, so this is clear from the graph as well, right? Next, move to the next problem. That is nothing but it is also the covering both the things. Okay, so this is the ridge pseudo inverse estimator. There is the two models. Okay, ridge model is theirs and pseudo inverse estimated is theirs. Okay, and combiningly we are using both the things. Okay, if we are using only the pseudo inverse estimator, then what will happen? If we are using the pseudo inverse estimator, then you will get the weight like this. Okay, so this is the weight. Okay, so in that pseudo inverse estimator, these if these the features are highly correlated, in that case this matrix will be non this matrix will be singular. Okay, non-invertible, right? If it is non-invertible, then that is nothing but the ill condition. Okay, that has the very small eigenvalues. Okay, if there is the small eigenvalues, these values will be, this gives the large value. Okay, if there is the small noise, in that case if there is the small noise, even that condition the weight will be huge. Okay, so one near zero eigenvalue can make the solution explode. Okay, so here the eigenvalues tends to 0. Okay, very small and tending to 0, right? Eigenvalues, and that is giving the large weight. And if that model for the small noise, even that the weight will be huge. Okay, so this is the condition for the pseudo inverse, right? To save from that condition, what we have done, we have used with that pseudo inverse with the ridge model. Okay, in that ridge model, this is the ridge estimator. What we have done, we have inserted the lambda items. Okay, by inserting the lambda items, what has happens? Okay, so it has got the stability, right? It is never be singular, right? It is always invertible matrix, right? If it is the invertible matrix, then the eigenvalue is go away from the 0, right? Okay, it is moving upward. Okay, so model is becoming the stable, right? So in the both the case, bias is excluded from the regularizations. Okay, so this is the case. So with this, so no eigenvalue is 0, inversion is numerically safe, multicollinearity is controlled, stabilizing the solution by shifting eigenvalues away from 0 by excluding the bias term from regularization. Okay, now see, this is the code we are running, this code. Okay, and after running this code, okay, so we will getting the weight. Okay, that is the weight we are getting, right? So this is the bias, that is the excluding term, and this is the weight in w0, w1 and w2. All right, so this is the case here. Okay, with the ridge pseudo inverse estimator, right? Now move to the next questions. That is nothing but the NRMSC and MSc. It is covering both the things, right? It is covering both the things. This is the NRMSc in here and this is the NRMSc in here. Okay, I will explain. This is the theoretical and this is the both the things I will explain, right? Practical and theoretical, just like I am going with it. Okay, so when we are using the NRMSE, this is nothing but the normalized root mean square error, and this is nothing but the normalized mean absolute error. Okay, so MSE, when we are using MSE, when we are using MAE, that is clear in the earlier questions, right? Now see, if the questions is if the situation is arises like this. Okay, some features are in say our salary is in 1,000, right? So some feature is in 1,000, another feature, as I want to buy the house, that time the house value is in lakh or crore, right? So that is the scale of the measurement is different, the scale of the measurement is different, right? So in that case, if the scale is different, okay, so we are doing the normalization means we are making the model independent of the scale matrix, right? So normalization, it makes matrix scale independent. Okay, an inference model computes prediction using the learned weights and optionally evaluates performance using normalized matrix such as NRMSE and MA to ensure scale independent error comparison, right? How we do it, how we achieve the normalization? So we have a data, okay, we have computed the residuals, right? So from the residuals we have got this RMSE and MAE, and we have got the Y max, Y mean. So RMSE divided by Y max minus Y mean, we will get the NRMSE, and Y max, Y mean, MAE divided by Y max and Y mean, we will get the NMAE. Okay, so this is clear, right? So this is basically using for the uh, uh, matrix scale independence, right? So here we will run the code. Okay, so here we will get the data, right? This is the data, okay, prediction, and this is the data. Basically what we are doing, okay, it is clear from it, okay, NRMSE and NME. Now let's move to the next questions, right? So this is the optimization, and this is over, and this is also, this part is over. Now we will move to the next, okay, bias variance. Here what is that, what estimator do you expect to be more stable, gradient descent or pseudo inverse? Okay, and why? I have explained these things, right? To pseudo inverse, what happened with the pseudo inverse, and what has happened with the gradient descent. Okay, so this is the pseudo inverse, that is the ill conditions, right? If it is the ill condition, eigenvalues is very small, it is tending to the weight will be huge, okay, and for the small noise, okay, small noise, okay, and weight, the assigning weight will be very large, okay, so that things will be arise, okay. So unstable model, we will get the unstable model here. When we are using the gradient descent, okay, we are getting the stabilization, okay, we are moving towards the stabilization, okay, and by using this reach and pseudo inverse, we have seen that the stability, how we'll get the stability in that explanations, right? When do the two estimators disagree and why? Yeah, though this is gradient descent and pseudo inverse will be disagree, all right? So in case see that there is the learning rate, and there is the ill conditions matrix are there, okay, and there is the regularizations, okay, and there is the stopping, right? So learning stopping is there. So in that case, these will be disagree with each other, right? So right, so in that case, that is the disagree with each other, that don't give a correct results, okay, right? Now we will move to the bias variance experiments, okay. So first, okay, right, yeah, we will explain that is nothing but the bias variance experience, okay. So in that show, she show variance shrink as n increases, okay. So there is a, in the sample, if the sample size increases, okay, then the estimated Gaussians, whether it is Gaussians or whether it is Laplacian, okay, if we are using the sample size, it means that the model is moving to the accuracy, okay, we are making the model more accurate if we have the uh, number of samples, okay, we have a huge number of samples, okay, but it is not possible. The population is 7 billion, so taking the data from the 7 billions, it is not quite impossible, right? So we have to take a sample, right? Sample is nothing but the representative of the populations, right? So if the n increases, then the Gaussian and Laplacians will be okay, will be converging. But what will happens, right? If we are using the Gaussian instead of the Laplacian, okay, or we are using wherever we want to apply the Laplacian, but we have used the Gaussian, then that time what will happens? Okay, so we will consistently achieve lower generalization error, okay. Mismatch losses converges more slowly, right? If there is the mismatch losses, then that losses converges more slowly if we are not using the proper model, right? Whether it is Gaussian or Laplacian, so it is these problems will be arise, okay. So these problems will be arise, so that's why we have to keep in mind that as you are increasing the sample size, it doesn't mean that the Laplacian and Gaussian error will be converges, right? So blindly we are using anyone, it is not possible. So this problem can be arise, okay. If you see this, if we run this code, then we will, okay, we will get the output, uh, come on, okay, here. Gaussian noise, okay, as it is increasing, sample size is increasing, it is a variance will be going down, right? Okay, so it is going down. In the Laplacian also the variance is going down as well, right? So in both the cases the variance will go down. So, okay, so but it is converges slowly, right? So you should keep in mind that things, right? Now we will show MSC beats MAE under Gaussian noise, right? Yeah, sometimes MSC beats MAE. When there is the Gaussian noise, then the MSC beats MAE, and then there when there is the Laplacian noise, then MAE beats MSC. Okay, so I have in that particular things I have explained these both the questions, right? I show MSC and MAE, okay, in this particular code, right? So Gaussian noise, for the Gaussian noise MSC beats MAE, and for the Laplacian noise MAE beats MAE. Okay, how it is happening, let's say, right? I have explained the concept MSC and MAE concept, I have explained earlier. Now see, when we are running this code, right? So this code is it is generating the output. Okay, this is generating the output. Okay, so come on, come on. Yeah, now you can see that this is the histogram, right? This is the histogram and this is the QQ plot, okay, and this is the kurtosis, right? So from the histogram, that histogram is normally distributed and has light tail, right? It is light tail, right? And this is QQ plot. You will see that the residuals is very nearer to that predicted line, okay, very near to that predicted line, and kurtosis is nearly equal to 3, right? So these three conditions are made. It means that the model, this means model is nothing but the Gaussian, right? So MSC is statistically efficient, so MSC is beating over the MAE, okay, right? Now if we change these things, right, okay, here you will, if you will change these things, right? So make this and activate this and run this code, then you will clearly find that this is nothing but, okay, all most of the residuals error are center around the 0, right? Yeah, okay, so most, and you will see that this is the long tail, right? It is the long tail example, right? If there is the long tail and most of the error are centered at 0, and here in the QQ plot you will see that the outliers are there, so some outliers are there. So for the outliers, if there are some outliers, then MSC cannot be give good result, we have to use the MAE. And if you see the kurtosis, the value is much more than the 3, right? So here MAE beat to the MSC, right? So this is clear from this code and this expressions, right? Now we will move to the next right, yeah, this is the next task, right? This is the next task. Okay, so regularization behavior bias variance data, okay, right? It is depend on the regularization strength. If the regularization strength has to be greater than 0, it should not be negative, right? If it is equal to 0, what will happen? Okay, if it is equal to 0, that time the weight vector is that is the weight vector. In that weight vector, this is the matrix, right? That matrix XTX matrix is ill condition. Okay, so here weight becomes unstable, right? Variance increases. In that case, variance increases and validation error also increases, right? Okay, so eigenvalue, here you will see that the eigenvalue is nearer to the 0, right? Okay, right, very small or nearer to the 0, right? In case lambda is greater than 0, then what will happen? Lambda is greater than 0, these terms will come into the picture, lambda I. It is never be a singular, right? It is non-singular matrix, it is in invertible matrix, right? So in that case, right, matrix become better condition, stable, right? Eigenvalue shift upward, right? Variance reduces, bias increases slightly bias increases, okay? So hence validation error is minimized at this point, right? Okay, this is nothing but the bias state. If we run this, and we have an explanation as well, if we run this code, you will see that uh, okay, run this code and then we will do the interpretation, right? It is okay, it is running. All right, see, this is the case, right? Here you will see that, okay, right, here is the unstable region here, and this is the stable region. Okay, it is the balance region, it is the middle portions. Bias and variance are stable, and here you will find that the okay, here cross validation error here is, it is increasing. Okay, it is the unbalanced, right? So in that case, see, lambda is equal to 0, then what will happen? So overfitting the model, here if the lambda is equal to 0, then the model overfitting, right? Model is overfit. Okay, so model is overfitting, it means that the variance, the high error is you will experiencing, and here the variance is high. Okay, variance is high over here. In the middle portion, the model is stable, right? Okay, bias variance balance. Okay, minimum error you will see, and in that region you will see that the high bias. Okay, this is the high bias region, high bias region, and low variance, right? If there is the high bias and low variance, so model is underfitting, right? So we will get the model underfitting. Okay, now right side, lambda is very large, then the coefficient string too much, underfitting, high bias, and error increases, right? Now L1 variable elimination. Generally L1 regularization eliminates the variables. So we have seen that things, right? It graphically we can see these things by running this code, right? So after running this code, we will see that this is the converging, the weights are converging, right? So this is as the regularization strength increases. If we are increasing the regularization strength, this bias will be okay converging, right? And at this point, okay, if it is touching, if the weight is touching here at this point, okay, then it will be 0. Okay, that will making the features eliminate, right? If we change likewise, see, if we copy these things, and if we make the value is equal to 1.0, right? So 4, okay, it's made that 7. Okay, there are the 12. Okay, and there are the 12 bit, and if you run this, then you will see that is converges early, right? Okay, so regularization strength we have kept the up to the 3, it is converges here, right? It is converging, and here it is getting 0. So variable is eliminated, completely eliminated here. Okay, so number of non-zero coefficient is 2. Okay, so correlated features and stabilization. So it is stabilization with L2. If now we have to stabilize the highly correlated features. How can we stabilize the highly correlated features? So highly correlated features can be stabilized by using the L2 regularization. Okay, how can we achieve that highly correlated and stabilization? If the highly correlation is there, then there is the instability in the model. You will see that the weight is there is the large changes in the weight, right? So when we are using the L2, there are the slight changes in the weight. Okay, we can see that by using the by running this code. Okay, just run this code very fast. You can see that the model is very correlated, right? After running that, without correlations, you will see that it is the shooting from 1 to 6, right? It is shooting from 1 to 5, right? After applying the ridge model, then you will see that the shooting is 3.060 and 3.035 for the x1, and 3.050 to 3.015. so the in the weight you can find that this very small changes. Okay, right? And then we are comparing this with the model, then you will see that okay, this is nothing but this is the ordinary least square. So and this is nothing but by using the ridge model, right? L2 regularization. So this, then that we are highly correlated, we are stabilizing with using the ridge model, okay, or L2 stabilization. right? Now this is the task, 5 tasks completed. Now we will move to the bonus task. Okay, quickly we will move to the bonus task. Okay, so time is also 11:59. Okay, so I have to submit this today itself and implement hover loss and compare, right? Yeah, this is nothing but the bonus point in the hover loss. We have to see that the when we have to use the MSC, when we have to use the MAE, okay, by analyzing the data, by training data, right? And we have to take like decision. But when we are using the hover loss, we need not worry about the MSC or MAE, okay, which one we have to use, okay, that automatically taken care by the Huber laws. Okay, if MSC, if there is the Huber laws behave like MSC when error is small, and Huber laws behave like MAE when error is large, automatically. So for residuals, this is the formula I have using R over here, and this is the threshold parameter, and that threshold parameters, okay, if R is less than the threshold parameter, it behaves like a MSC, and if R is greater than the threshold parameter, it behaves like a MAE, okay, automatically, right? So if we are running this code, then we will get the idea, right? So here we will see that OLS line is pulled towards outlier. Okay, yeah, this is nothing but OLS, okay, it is pulling towards the outlier, and this is fitting to the okay, this is okay, closer to the true slope. Okay, this is nothing but the Huber loss, right? This is the Huber line, and this is the OLS line, this is the Huber line. Okay, right? Huber ignores extreme points, right? Then manually we are running that the course, then the Huber loss is coming out this one, that much. Okay, right? And then the if you see the gradient distance manually, then what will be the behavior? You will see that that is nothing but the Huber line, and this is the behavior. Okay, so Huber loss during training will be going down. Okay, so it's all for assignment number 1. I have covered everything, but some minutes are extended, so I hope sir will allow me. So it's all for the assignment. Thank you.